Cool. So hey, everybody, my name is Willem and I'm presenting Rethinking Feature Stores. So I'm creator of Feast, created that at Gojek where I led the machine learning platform team. I'm now a tech lead at Tecton. So let's get into it. Okay, so I'm going to start off by just discussing, feature stores and their origin. Feature stores started at Uber. The team at Uber built Michelangelo platform 3 years ago. At the time, they recognized the importance of tooling for features and the impact that I could have on production ML systems. And that awareness led to the development of a system called the feature store, and they coined the term. So I wasn't involved there, but I currently work with a team that actually initiated that project. And the feature store was a central hub for managing data flows for ML applications, and it allowed teams to rapidly create and deploy machine learning features from raw data, so whether batch or stream, and reuse those across projects. And those features became the foundation for machine learning systems that they built. And the reason this is important is because what we built with Feast eventually was modeled almost entirely on this platform, this Michelangelo platform, because they had blog posts that went out and they went into a sufficient amount of detail that you could understand the motivations and then model. Sorry. You can understand their motivations and then model your design after them. And so a category was essentially created, I think it was 2017 that they released that, and we built Feast in 2019. And they've also then left Uber, some of those creators, and then founded Tecton. And so there are many feature store startups. At least in the last year, I can count numerous amount of them. So we have, like, in this case, my employer, Tecton, a fully managed feature store that we're building there. We've also got open source feature store Feast. It's a great option if you just want to get started on open source tech that you can deploy yourself. So today we're going to be talking a bit about both. So the agenda for today is talk about what's so hard about production ML, productionizing machine learning, anatomy of a modern feature store, and then I'll show you a quick demo of the new Feast. So what's so hard? Why is productionizing ML so hard, and especially on modern data stacks? So the first thing to define is, what is a modern data stack? So these modern data stacks are defined by primarily cloud data warehouses or latest generation of data lakes. And they've risen in popularity over the last couple of years. So these modern data platforms are offering data teams good solutions to centralize their data, to reliably clean and aggregate that data into a useful form, and to share it for analytical purposes. So really, they enable analytics that are self-serve, near zero maintenance, and scalable. And that's revolutionized how analysts and analytic teams can unlock insane productivity. But what about ML? If you're starting with ML, you need to look at two places. You've got your model training, and that typically happens in an offline environment or in a pipeline somewhere. Let's just assume that it's a Jupyter notebook. But you also need to have an online system, or in some cases you can do batch scoring, but in a lot of cases you've got a production system that needs to make inferences or predictions in real time. So you have to deploy that system into a production environment. So you can think of something like a fraud detection system, a recommendation model, and you need reliable access to fresh feature values that for making those predictions. So both training and serving need to access feature data, but really what is important is that you have consistent access across these two environments. So where can we get features for training? So ideally, we can use the high-value refined data from these data platforms that a lot of teams in the organization are already putting effort into creating rich data points, and you can just reuse those. But it's not always that easy. And we've been talking to a lot of customers and users over the years, and even if you have technology that enables this, there are other problems with it. So one is you don't have all the data in the warehouse. So often teams won't ship all the data from prod into your warehouse. So it's just a security reason. They limit the information that is available to teams for analytic purposes. It's just siloed. And the data that is available is often not in the right shape. So it's typecast or downsampled or reordered. It doesn't have the characteristics of the unordered, unstructured data that might arrive at your production system, even if it's quote unquote raw. Okay, so where can we get features for inference? So the, ideally, we'd want to use the data there in the data platform for inferencing, but it's also not that easy. So the characteristics of a data platform don't really allow real-time serving, doesn't have streaming support. I mean, you don't have even the transactional features or data points available there because they're not synchronously written into the stores. That might be an async process. But probably the biggest reason you can't use a data platform in the production environment for ML is production engineering teams typically don't build, or they don't trust the data platform, and they don't build systems that integrate directly with a data platform, or like, let's say, a BigQuery or a data warehouse like Redshift. So those are often used, one's for analytics, one for production, and there's just a trust gap there. And so they typically don't do that integration. And sometimes you don't even see staging, dev, and prod separations in data warehouses, where you do see that in the production environment. So a lot of teams face this trouble connecting these two. So the challenge isn't in connecting offline data to production, it's in managing the complexity of ensuring consistent data access across environments. So for ML teams to be fast and effective, they can't be dealing with the complexity in every iteration loop. They need tools and workflows to be able to iterate quickly on features and have them easily available for training and production inference. And the correctness of ML systems depend on getting the same data inputs across environments. And dealing with that complexity is I'd say the biggest problem, but it depends on how you're looking at it in productionizing data for ML, and why it can take teams months to get a model into production. So in the real world, many teams fail because they build short-sighted solutions or workarounds to these problems. For example, let's just dive into one of them, and it's very common for teams to rebuild their offline training pipelines in production, and not necessarily because they want to, but because they don't really have choices. And so you often see in them Spark and Flink and Cassandra and a lot of these technologies that data scientists don't have in the offline training case, or re-implementing a lot of the transformations and a lot of the data processing pipelines in the online side. But these are disconnected systems built by engineers and often not by the data scientists. So firstly, the iteration loops are very slow and painful. It's error prone because there's data inconsistency because you're running two separate environments and pipelines that are redeveloped. The transformations are redeveloped, and even the infrastructure is different. But probably the biggest problem is just engineering teams need to be involved. And what ends up happening is that data scientists are not empowered to go end to end with their ML solutions. So they don't control the complete life cycle. So they have to speak to engineers to get to prod, and this just slows down their development cycles. So their outer loop development cycle is an order of weeks or sometimes months. Just because engineers by nature don't want instability, they want to deploy something, rein in the entropy and have that system just stabilize. And data scientists want to try new things and experiment. So really doing ML right is about bridging these two worlds. And how can we make productionizing ML be as easy as just building a dashboard for a warehouse and unlocking that high productivity that analysts have benefited from previously? And so the answer to this from our side is the feature store. And feature stores are the hub for data in an ML for ML applications, and they're really focused on solving the data complexities of putting an ML application in production. So that means ensuring transformations are consistently applied across environment. Data is organized for machine learning. Features are accessible for training and real-time inference, and there's monitoring and validation of data going to models so that that it's only high quality models, at least high quality data, or at least consistent data being fed to models. And there should be a simple workflow for teams to quickly iterate. So it shouldn't just be a heavy infrastructure system that is a black box. So, and feature stores don't just do this by duplicating your whole stack. It's not a new platform that you have to deploy. And I think it's a very important point to make that feature stores extend your existing infrastructure. So if you're running an offline store like a BigQuery or a Snowflake, feature store should be extending that and reusing the infrastructure that you have and integrating with your existing workflows in order to make you more efficient. So it's not about deploying a new new piece of infrastructure. So let's talk about the anatomy of a modern feature store. So the typical components, so I'll dive into like the high level areas that we typically see in a feature store. The first one is serving. So, if you have a production system, you need to be able to retrieve features. Often these are just key value, low latency feature lookups that you need for inferencing. And we're just going to assume that one of the highest value props for feature stores is in the online case. If you're just doing batch, yes, you can still get value from it, but most of the use cases we see are the online ones. So you need an online serving layer to retrieve features online. Then you also need to be able to train data. And for that, you need to be able to export data sets from a feature store. Of course, feature stores need to plug into your existing data. So you can look at, you need to be able to integrate with streaming sources, batch sources, operational DBs, vendor APIs, flat files, public data sets, whatever. We need to be able to integrate to those in order to join those and create training data sets. And for the first primary component is the serving layer. And so the serving layer really integrates or combines the two types of serving, the contexts of training and serving. Models require this consistent view across training and serving. And so that single unified serving layer is a really critical part of this consistency. And it's the consistency is, again, not just training and serving consistency, but it's also cross environment. So dev, staging, prod consistency. You should be able to promote a feature across those environments so that you've made a transformation in development, you should be able to get it into production and without it failing halfway through. And the feature store is responsible for ensuring that the transformation you've created is portable across environments and contexts. So in some ways, it's representative or comparable to Docker containers at an abstract level. So the second component that's quite important to know about is the storage layer. And so feature stores contain both an online and offline storage layer to support the requirements of different feature access patterns. The offline storage layers are typically used to store months or years worth of feature data for training purposes. But extending an existing data lake or data warehouse for offline storage is typically preferred to prevent data silos. Online storage layers are also used to persist feature values for low latency lookup. So they typically only store the latest values, and you can think of like Dynamo or Redis. Those are typically used for online stores. Feature stores typically use also an entity-based data model where each feature is associated with an entity like a user or a product or a driver and a timestamp. And this makes it possible for us to do point in time or as of joins. And what you'll find also very frequently is that feature stores are primarily time series based data in order to do this point in time based lookups and building training data sets. And you'll also find, just as a digression, very few computer vision or NLP being done or deep learning being done through feature stores for that reason. So many feature stores are actually run, but many feature stores actually run the feature engineering transformations to convert raw data into feature data. This happens by orchestrating transformation jobs on your existing infrastructure. So, for example, on your warehouse or your Spark cluster. And many types of feature pipelines are expensive and needed to be pre-computed before usage. The feature store handles the regular recomputation of feature values and automatically backfilling historical values of newly developed features for model development. So in the Tecton case, we've got, and this is an extremely core part of our IP, but in the Feast side, this is something that we didn't really have at all. Feast doesn't do backfilling, it doesn't do feature computation. But for a lot of teams, this is critical. And I think for Feast, this is something that we bolt onto your existing system and expect you to have the ETL already. Monitoring. So as the layer between models and data, feature stores will play a critical role in ensuring the operational reliability of production ML systems. So feature stores are able to produce metrics and logs that allow teams to observe the quality of data served to their models. But by being the interface between models and data, feature stores organize all of this data, and that is important for model operation, but also model debugging and auditing. So modern feature stores not only do basic data quality monitoring, but are pluggable into external monitoring systems. And inside of Tecton, we're also working with a lot of these integrations right now, and this is going to be a big focus for us as well with Feast later on in the year. So feature stores not only extend the monitoring of and data quality, but monitoring data quality, but also they produce operational metrics that allow you to track things like cost. And if you're watching the Apply conference, there's a talk by Atlassian on how they use the feature store to track cost. And I'd encourage you all to have a look at that. Then finally, the feature registry is the central interface for user interaction. It acts as a single source of truth for information about features in an organization. So the registry contains feature definitions and metadata that users can use to discover new features, collaborate, and just ultimately reuse features. But the feature store also informs the behavior of computation. So, the feature registry. So the feature registry can be used by the job scheduler in order to do backfills. Like it will go to the feature registry and understand the desired state of the feature store based on what users have defined and registered, and it'll run and schedule those jobs. And so the registry is a really critical piece to understanding, what the feature store's desired state should be. And you don't just track feature definitions that are kind of immutable and version and stateless, but there's also state that's often tracked there, which materialized intervals have been computed and things like that. So the registry is the state or the metadata that is essentially going to be underneath a user interface that you used for discovery and sharing. Yeah, so just to wrap those up, so it's serving, storage, transformation, monitoring, and discovery. Those are the 5 components that really make up the feature store and ultimately make it the hub for data flows of ML applications. And so let's talk a little bit about some of the things that we've seen, if feature stores evolving towards. One of the things that we've seen a lot of people ask for, and what we're going is making feature stores lightweight. And one of the things that we're really focusing on over the last, I'd say, year or so is just making sure that feature stores really integrate with your existing cloud infrastructure. So, a lot of folks we speak to don't want to create data islands or data silos, and introducing feature stores solves one problem, but it introduces others. And so, feature stores, with modern feature stores, we're not going to build a new database. We're not going to expect you to create or use a new DSL or deploy a new Spark cluster or key value store. The modern feature stores, reuses your existing clusters to run transformations, or reuse your online and offline storage layers, and it will just add new data or new tables or new schemas there in order to provide you an opinionated and a structured way in order to execute certain workflows that are machine learning specific. And a lot of the existing data tooling that are available to us on cloud providers already are sufficient for executing these operations. But the challenge is in the best practices that the feature store, or the abstraction that the feature store can enable on those technologies, not reinventing databases. So I think another thing that's super important for a lot of teams is, okay, how can we make feature stores incrementally adoptable? And they often start off with, they've got their disparate pipelines, they've got a training pipeline and some kind of system that's feeding streaming data to their online systems. But what's important is, how can they incrementally adopt new feature store and extend those production systems and get an immediate win? And feature stores are not all or nothing. They're incrementally adoptable. You don't need to rewrite or migrate your existing feature pipelines to begin using feature stores. They're built to work alongside any existing infrastructure that is already built and working, that you're already happy with. So it's a common pattern for teams to start using feature stores to get new features they've always wanted in production without having to think about migrating a bunch of working stuff to a new platform. So the diagram I have on screen is just you deploy a feature store on the side, and then you can just read those features then in the 2 environments and just join that onto your existing inferencing or training steps and start benefiting from it immediately. But what a lot of teams then find is that the clean abstraction, the single interface for reading data, is actually very useful from an operational standpoint. If you could decouple your serving or your model is training and serving layers and your data production stages, then you've got a very clean abstraction and decoupling there. And so what they end up doing is they feed their data into the feature store. They've got Spark pipelines or whatever they're running Airflow into the feature store, and then they use the feature store as the single source for retrieving data. And that doesn't mean you need to rewrite your ETLs in a new DSL or anything. Most feature stores have an ingestion API. We can just load batch data. Cool. So just to kind of wrap up this stage of the talk, so one of the things that we realize that a lot of ML teams are spending a ton of time on data flows for their ML systems. It's probably the biggest problem still. I guess we're not going to solve it in the next couple of years, but it's something we're very focused on. But at Tecton, we've built a lot of elegant solutions to these problems. And we really want to help ML teams do this well. And we're working towards major contributions to Feast. And we've already spent a lot of time over the last couple of months making Feast easier to use and lighter weight. But over the next couple of months, we're going to be doubling down on that effort and open sourcing more of our technologies. And we're hoping that over time, the Feast project can become an open standard for a pattern for teams to deploy feature stores. So check it out after the talk, and hopefully we can get some contributions there, or at least start a discussion. So I'm going to quickly introduce you to Feast 0.10. That's one of the latest releases that we just cut last week, and show you a quick demo. So Feast 0.10 at a high level. So the feature store principles that I just and capabilities that I just talked about, they form part of a broader vision that we have for feature stores. But the 0.10 release that we just cut last week is the first milestone, but it's specifically this is the first milestone towards this vision, but it's specifically focused on serving one area of the feature store capabilities. So our goal with 0.10 was to make the simplest and fastest feature store for ML teams to productionize their data. And the 0.10 release is just focused on 3 areas. It's much, much smaller in surface area to a large platform like Tecton. So focuses on training data set generation with point-in-time correctness. It also provides online serving with online key value store with Firestore or SQLite, and it provides consistency between these environments. So it provides a consistent interface to retrieving features for training and for online serving. And that abstraction is one of the things that teams find very valuable. So this first release is only focused on, it only ships with BigQuery support and Firestore support. And of course, you've got the open source technologies like SQLite and Parquet as well, if you just want to play around with it locally. So Feast 0.10 makes it easy for teams to deal with the complexity of consistent data across environments. And just to quickly recap some of the key aspects or the key changes with 0.10. So it's zero config. So if you're just a small data team or you're just getting started, we're giving you an opinionated way to deploy the feature store so that you can just get started in seconds. Feast 0.10 ships with the local mode, meaning you can test your end-to-end workflows completely locally. So you don't have to have any cloud infrastructure or any internet connectivity. It runs standalone and doesn't even need Docker. It's just all Python, the local mode. It has zero infra if you're just getting started. So 0.10 doesn't require Kubernetes or serving APIs or Spark. You can just run everything with serverless technologies or locally, but you can also deploy it on Kubernetes, and you also can use Spark if you want to use that, because that was the basis of the old Feast or the previous release of Feast. And finally, Feast 0.10 is also way more extensible, and we've added a provider model that allows teams to easily add new data sources or storage engines or compute, and make that super easy for folks. So I'm going to show you a quick demo of the new Feast, just quickly how to set up a feature store, train a model. I'm just going to use scikit-learn. It's going to take a few seconds. We're going to test out that model with SQLite DB. It's going to be all local. And I'm going to show you what it looks like if you read features from an online feature store and how we can quickly productionize an online feature store. So let me just quickly flip over here. Can you guys see my screen? Hopefully this time it's working a bit better.
Yep.
Okay, cool. Okay, so the use case is just, imagine you're going to productionize an ML model. You're going to receive a list of driver IDs, and you just need to predict which driver is the best suited to complete a trip. So we want to optimize for likelihood of completing a trip. And of course, you want to use an ML model for this. So let me just clear my screen. You know that you have data on drivers, and so let's query that. And what you want to do is you want to train a model, and then you're going to use a model when these driver IDs come in to make a prediction on which driver is most likely to convert, and then send back the highest ranking driver. And so you've got a historical data set called driver hourly stats, and you've got conversion rates and acceptance rates and daily trips of these drivers, and you think that's probably good, good features to use. So the assumption here is that there's a system, an ETL system producing feature values in your organization already. What you want to do is just use that data to train a model using feast as the abstraction. Then we're going to test that model locally with a local online feature store for prediction, and then you're going to ship your model into production, and then you're going to deploy a production feature store, and those things together will be able to end up as your online stack for inferencing and choosing the best driver. And so how you do this with feast is you'd first go pip install feast. I've already done that, so we don't need to do that again. And we're going to just initialize a feast repository, and you just need to run a feast in it in order to create a repository. And if you look at the top left here, let me just show you what this folder looks like. It just has two files, a driver repo and a feature store YAML. The feature store YAML is simply a file that describes the infrastructure that your feature store will be deployed on, and just some basic infrastructural configuration. In this case, we want to do some local testing. So let's just set this provider to local. The provider just sets the infrastructure target. So it's local or GCP, it could be AWS in the future. The registry is the place where you're going to store your feature definitions, and the project is a namespacing. It's just a name that be for namespacing. Okay, so we've got that set up, and let me show you the driver repo. So a repository in Feast is a collection of Python files and feature definitions. So that can consist out of feature views, sources, and entities. And this just basically describes to Feast where it can find information and how it should represent that information in a database agnostic way. And so now we're just telling Feast there's a table with driver stats. The primary key is the driver ID, it's the entity, and these are the features that you can find there, and these are some of the characteristics on how we can retrieve that information. And so when you register this feature definition, Feast can then materialize this information for building training data sets or for materializing into the online store for serving at low latency. So let's just quickly go over into this repo and then run Feast apply. And so Feast apply works similarly to how Terraform apply works. In this case, it's registering these feature definitions, but it's also provisioning infrastructure. And so we've set the provider to local. And if you look at the top left there, we've got a registry. And this is a protobuf registry. You can already access it, but it stores your feature definitions. And you've got an online DB. And this online DB is just SQLite. And so this is great for testing because you can run your local development end to end without having to deploy anything into production or into a cloud environment. So this online DB is empty right now. Let's just load some feature values into it. So we use feast materialize incremental, and this will load from BigQuery, export feature data for each driver, and then load that into the key value store, into the SQLite key value store. Okay, so we've just loaded that data in. And now what we can do is we can train a model and we can ship it into, or we can then test it locally with a SQLite DB. So the first thing we're going to do is go over to our training data, training Python script. And I'm going to show you what the abstraction looks like from a training side, training point of view. So here, all you need to do in order to export data from Feast is you head over to, you import Feast and you create a feature store object, and ensuring that you're pointing this object to your feature repository, the driver ranking repository that we have over here. And from that, we can infer where the registry is, and we know where the data is. And so if you use this object to just get historical features, and you provide a data frame, and so in this case, we're providing an orders data frame, Feast will join feature data from all of these feature tables. So we've provided the driver hourly stats table. It'll query that table and then join these together in a point in time correct way. So it's going to reproduce the feature values at the specific points in the history, so that it's representative as to the online case. So it'll be the same as the feature values that you'll be seeing online if you had streamed them in at low latency. So we're just going to run this, and it's going to export a pandas data frame. We're going to train a linear regression model. I'm just going to start this up. So we're going to train a linear regression model, scikit-learn, and we're going to save it out to the driver model bin file. And so one thing that's very important to note here is that you can provide any amount of types of feature tables. So you can have like another one that's like, customer something, and Feast will intelligently join those based on the entities that you've provided and construct this data set for you. And so this really takes a lot of the issues away with feature leakage, because data scientists don't have to do point in time or as of joins. So we've just trained the model, and if you see on the left there, you should see a binary. And we could just head over to the training, the prediction script. And how we would then test this model is you typically deploy it like some kind of class that does inferencing, maybe using MLflow or Seldon or something like KF serving. And you'd load a model in, and then you'd need to have some system providing online feature values. And so what we've got here is we can just use Feast for that. So in your initialization for this class, for the driver ranking model, you load your model binary, and then you load a Feast, you construct a Feast feature store object, and you point it to your repo. And then when driver IDs come in for prediction, you do a couple of things. One, you just read feature values from the online store. So you send those driver IDs with a list of features, and these are the same features you use for training over. And when you call this get online features method, we're just reading straight from SQLite. So because we're in local mode, we're just going to read those features straight out of SQLite, and then that'll be available for prediction. Remember, those feature values came from BigQuery, and so presumably those are the latest known features for those drivers. Then we can use that data to predict using the model that we just trained, which driver is the most likely to convert, which one is the most likely to have a successful trip, choose the best driver, and return it. And so if we run Python predict, we should see a value coming back. Yep, 1001. Okay, and now obviously this is just a locally running feature store with a local model. How can we productionize this? We just head over to our feature store YAML file, change it to GCP, and then run feast apply. And now we're going to provision infrastructure. And this is where it gets a bit more closer to Terraform, in that it's migrating tables. It's actually creating Firestore tables on Google Cloud. And so we've got a new online database. It's running on the cloud, and we need to materialize values into that. And so we just run materialize incremental again, which queries from BigQuery and then loads back into the online store. And then, okay, values have arrived. So now we have values in Firestore. And the cool thing is now that if you just rerun all this code here, your prediction routine, it'll just work, because your feature store changed, but your model serving didn't change, and it didn't have to change because it finds its information from your feature store configuration. And so there we have it. So you've got Python predict providing the same values. And if you ship this class into production, you've got a completely production feature store running on serverless tech, and you don't have to manage any infrastructure. There's no Kubernetes, no Spark, none of that. It's just a bucket and a serverless online store like Firestore. So that's pretty much the demo. And just to recap, we set up a feature store, we trained a model using BigQuery data, and then we tested it with SQLite locally, and we tested against online DB with Firestore. So what's next? Right, so today we have two products. There's an enterprise feature store with Tecton that has advanced functionality like transformations, access control, UI, it's managed service, and you get production SLAs. And on the other hand, you have Feast, where it's completely open source. You can deploy it yourself. You can get started with this and run it yourself, but you need to do a little bit of work there, even if it's easier than it was in the past. So what we're working towards is a common standard for feature stores. And this 0.10 release is the first step towards that. But over time, we want to converge our APIs and work towards unified specification for feature definitions. So what you can expect is more technologies from Tecton to be open sourced to Feast, and then also the possibility for us to move from, or users to move from Feast to Tecton if they want a managed offering. So that's the end of the talk. And if you want to try out Feast, check out our quick start. It's on our docs. Feast 0.10 has been released. If you want to run Feast on Kubernetes with Spark, that's also still available. The 0.9 release is up and running still. Check out our Helm charts and installation guides. And if you're looking for a fully managed service or a fully managed feature store, come and chat to us at Tecton AI. And you can also reach out to us on Slack. We've got the supply conference that's live right now. Over the next 2 days, we have like over 1,000 people that have joined our Slack in the last 48 hours. So we're all there asking questions and having it's like just great conversations on data and applied data for machine learning. So yeah, that's it from my side. And I hope you have a lot of cool questions from you, interesting questions.
I have a question. I saw somewhere that Feast was available on GCP. Is that
That's right, yeah.
true? Okay, cool. You know how we'd find it?
Find
Oh,
feast.
yeah, in
Oh,
GCP. I was looking for it for the other day and I couldn't
you mean
see it.
on in the marketplace or somewhere
Is it
else?
market? Okay, maybe that's
No, no,
where.
no. I'm asking a question. I'm not
Yeah,
sure.
yeah. I wasn't sure where to look. So,
Oh no, I mean you can just deploy to GCP. It's not something
okay.
that's available on the interface itself. But I know
Okay,
that yeah
cool.
the cloud providers are all working on their own feature stores. So I'm not sure to what extent the components are being reused behind the scenes.
Thanks.
Yeah.
Yeah, question. You mentioned that you're hoping that Feast is going to be like the next generation is going to be like an open standard.
Yeah.
You also said that cloud providers are working on their own feature stores. How much buy-in do you have around this open standard? Because like from my perspective, I mean, that would be amazing if we could all agree on something moving forward.
There was a great talk that we had with David Aronchek on this from Kubeflow. I think it was on MLOps community a while ago, where he said that it's very hard to get full capital S standards created so early in the wild west stage of a category like feature stores. So it's unlikely that we can do that very soon. The Google Cloud, and there's like all these Google Cloud and Amazon and Databricks. Probably they will all have their own solutions, and many of them speak to us frequently. But it's very hard to get that convergence on day one, and probably that'll only happen if there's a dominant feature store that shores up most of the market. So the conversations right now are happening frequently on standardization, but it's typically large companies that their market isn't to sell feature stores, but they want to solve a different problem. And a feature store is just something that enables some kind of product that they're trying to sell or service they want to deliver. So there are a lot of conversations happening around standardization with those teams and us, not so much with cloud providers. So I'd expect cloud providers to just do their own thing, and eventually, if Feast takes off or another feature store takes off, they might be forced to standardize on those APIs.
Got it. Thank you.
Yeah.
I got it. Sorry, go on, Keith.
I had a question. When you were talking about being able to do these things serverless and not requiring things like Kubernetes or Kubeflow, what solutions do you see as especially promising for when you do want to automate pipelines and do things on a recurring basis?
I think part of the challenge is, well, okay, firstly, Tecton. You really laid that one up for me. You mean for the general purpose data engineering challenges, or for machine learning specifically?
Well, you've laid out a really good case for what you do when you want to experiment and then test what you've experimented on. But if you want something to be retrained every day, automating that process and what infrastructure you set up for that.
Yeah. Honestly, we haven't found a good solution, and that's part of the challenge. That's probably why we've built a lot of our own in-house Tecton. So we've run Airflow and a lot of scheduling tools, and we've used a lot of like data processing tools in the past at Gojek, and there was no silver bullet. So I don't really have a good recommendation there. Yeah. So everything we built at Tecton was pretty much custom made.
Thank you.
And of course, with Feast, there's no scheduling, and there's no computation itself. So that's not a problem that the project currently solves.
Is Feast mostly tabular data right now, or is it gonna be
It's
extended to
almost,
unstructured?
yeah. So mostly feature stores are tabular. We've got advanced types there, but the value of the feature store is really degraded if you just have like, n-dimensional array of bits or bytes, right? So cataloging that and adding intent and metadata about that or semantics really doesn't add, it doesn't become parsable, right? So it's mostly tabular, you're right.
Fitz has a question here. He says, early on in the talk, some of your descriptions sounded like what might be covered by a data virtualization tool, connections to lots of data abstracted. Does Feast work well with any data virtualization tools or replace them?
Well, honestly, I don't have a lot of experience with data virtualization tools, but I think the key thing to note is that the characteristics of the retrieval characteristics and source characteristics across training and serving are often different. So, you have real-time data that you need to be able to access at low latency, and they're coming from streams. And then if you have large amounts of historical data that you need to produce training data sets with, and you need to scale out the compute, across multiple nodes in order to even build those training data sets. And you have to do things like, move them on like, HDFS or buckets or something in order to distribute, compute for training, right? So I don't know if data virtualization does that. That would be pretty amazing if it does. Yeah, sorry, that's one answer. It'd be interesting to find out more about that, and if we can get some inspiration from those technologies.
Do you have any plans to integrate with Snowflake?
We do, yeah. That's something that we want to focus on very soon. So Redshift and Snowflake and Dynamo will be the connectors we ship soonest. Yeah, and of course we have Redis support, but we haven't ported that over to the latest release.
Like, what's a good rubric for people thinking about when to store data in a data warehouse versus maybe a NoSQL or a key value store?
Well, I mean, it depends on what the use case is, right? So I think the world is heading towards data warehouses. So I would say, just double down on the data warehouse as much as possible. Keep things simple, keep things centralized and aggregated. But if you need to serve at low latency, and you have this disconnect between your prod and your data warehouse analytic environment, then a feature store becomes kind of important, or at least some unified abstraction that even if you have to build it yourself. Yeah.
Any other questions? I have another question. Like, when is there a point when a company or a team might be too small to use a feature store?
Well, in the past, I would say, if you need multiple use cases or more than one iteration of a specific model, like it could be something really important to your organization, like an ad prediction model or something, or like some kind of ad-centric model. But what we're going with Feast is that a single data scientist should be able to deploy the system and get it live, or a data engineer. So we think that there is a use case for is one person, we call them solution teams, solving a specific business problem, as opposed to platform teams being the only teams deploying feature stores, which was the pattern we saw in the past the most frequently. Yeah.
Cool. Any other questions? Well, this has been great. Thank you very much.
Cool.
So yeah. Awesome. And I'm going to drop a link for apply in the chat here whenever it loads. Sorry, I have to get rid of your email tracking. So. But who's speaking tomorrow?
Honestly, I am not sure which ones are up tomorrow. We do have one from Provectus. They'll be speaking about Feast on AWS. That's what I'm looking forward to as well. But I haven't looked at the agenda today because they did switch some of those around. So I'm just not 100% confident.
Yeah, some great talks today. So if y'all want to see some great talks tomorrow, then go watch the live sessions. So well, cool. I'll stop recording and I'll leave the room open for a bit if anyone wants to chat. So all right, thanks again, Willem. It's been awesome. So,
cool.
Thanks. Awesome.